Stockholm this morning, Miguel Zumalacárregui, that will talk about dark energy at the speed of gravitational waves.
Thanks, Martina. So, yeah, I'll be talking about dark energy, so it's a bit of next week topic, but also how to test dark energy models and what I think are interesting dark energy models using gravitational waves. And this is, as I'm going to show, it's going to be a very drastic, very dramatic test. So it's sort of all of nothing for a very broad class of dark energy models. So as any of you, I'm very excited for this new era of gravity in which we have observations of black hole binary coalescence. We have very precise measurements of these violent events, and I have no doubt that this is going to be one of the huge things that are going to happen in science in the near future. And I think that we're going to learn a lot of stuff from these kind of events, particularly about gravity. Strong field gravity, black holes, their life and death, and also perhaps about dark energy and dark matter, as some people have been working on, the idea that black holes could be part or most of the dark matter, etc. And of course, we are in an era of extraordinary advance for cosmology. We have a series of extremely good surveys in different frequencies, different objects that are converging into very solid, very predictive, and relatively simple standard model of cosmology. And this convergence goes with the price of having a big chunk of what makes up the universe made of dark matter, some form of matter that we have yet to detect, and even a larger fraction of the pie made of dark energy, so some sort of energy density that accelerates the expansion of the universe. And now we're working hard. These two things we can only detect through gravity or through their indirect effect, and we're going to be working very hard on a series of cosmological experiments and galaxy surveys that are going to map the universe and get a lot of information to try to constrain these components as best as we can. Now, not everything is sweet in this standard model. There is a very uncomfortable tension. Well, there are a couple of things, but one that has been evolving over the years, and it's sort of becoming serious now, is the determination of the expansion rate of the universe. And there's basically one measurement that consists on measuring Cepheids and using them to calibrate supernovae, and then knowing the intrinsic luminosity of supernovae, constructing a Hubble diagram at low redshift that gives a rather high value. And on the other hand, we have a very precise, although indirect, inference from the cosmic microwave background combined with other probes like baryon acoustic oscillations, and assuming the standard lambda CDM paradigm. This gives a value that it's lower. It's about 3.4 sigma away from the direct measurement. So of course, there is the chance that one of these teams have some systematic effects, that there is something fishy going on in the analysis. You might have noticed that there is a lot of papers coming out recently to try to explain this. So it could be that there is some systematic effects, but it could also be that everybody's doing their job right, and we might be witnessing the first hints of new physics from cosmology. I'm not going to talk about that, but there are also some other tensions, particularly weak lensing surveys that also seem to point to something being different between the early and the late universe. And so since it's the last talk of the day, I'm going to start by showing you my main results so you can decide whether you want to pay attention till the end or just get this brief summary. So I'm going to present a very relatively simple, highly testable dark energy model that has the nice virtue of naturally explaining the high value of the Hubble rate measured by local observations with doing the fit to the CMB. And you can see this in this plot. The price to pay is that you need to have massive neutrinos in this model. There is some tensions with other data sets, but I think it's at least an interesting first step towards a dark energy model that can solve this problem. And now, as I said, it's a very testable model. And one of the consequences that it has, it's rather surprising, but it unambiguously predicts that the speed of gravitational waves is going to be different from light. And this is huge, because this is a number, the speed of gravitational waves, that we can, in principle, measure to an extreme precision. And this could be a spectacular ruling out of this model, and it could happen very soon. So, to start, of course, this is a dark energy modified gravity model. So I would like to at least mention 3 reasons why I think it's interesting to consider alternative theories of gravity. One is, of course, cosmic acceleration. We believe that the universe started in a cosmic accelerated era. We know that that era was not caused by a cosmological constant because of the primordial perturbations and how they run with the scale. So it's not crazy to think that something similar or related, even related, might be going on. The second reason is purely theoretical. You might notice, if you go to Wikipedia, there is a very interesting page on unsolved problems in physics, and about 1/3 of them have something to do with gravity. They go from quantum gravity to dark energy to the origin of the universe, and dark matter, etc. So it might be that studying these theories that might seem a bit crazy, we might learn something interesting, or even end up with models that are explain some features more at the theoretical level. Of course, my primary motivation, the third one, has always been to test gravity. If we can test gravity, we should be doing this in any regime that is accessible. And we do this by confirming standard predictions, or also by ruling out competing theories. And to rule out competing theories, the first step is to find interesting candidates. So, in a nutshell, general relativity, Einstein gravity is very well tied down by some theory principles. So in order to go beyond, we need to change something, either add new ingredients or lift some of the assumptions. One very interesting possibility that was developed to a large extent here is massive gravity. And this is a very tough problem in which there was very significant progress recently. But still, despite a lot of work and a lot of enthusiasm, we don't have cosmological models based on massive gravity that make any sense. So I'm going to go with the simplest case of just adding one scalar field and see what we can do. And it turns out this is a very old idea. The first generation of scalar tensor theories started by Brans-Dicke theory, and then we can add generalizations, were proposed already in the 60s, studied very extensively in the context of solar system tests of gravity. But that's, of course, just the beginning. There is a second generation of scalar tensor theories that was proposed in the 70s by Grigory Hordensky, at the time a PhD student. Hordensky eventually quit physics. He became a painter, has these very psychedelic paintings of plants and the desert. He lives in New Mexico, very nice guy. Well, Hordensky's theory is the most general scalar tensor theory compatible with what we believe nature respects, and that is described by second-order equations of motion. And this is a technical requirement that is sufficient to guarantee that there are no additional degrees of freedom. This theory allows us to add up to 4 functions of the scalar field and its derivatives. These functions, of course, include the first generation, things like quintessence, and of course Brans-Dicke, f of r, chameleons, all these old school theories. But also we can add, sorry it's a bit dark, interactions that involve the second derivatives of the scalar field. And there are several of those that have a very restricted form. And they typically involve derivative interactions between the curvature and the scalar field. So I'm going to be talking about these theories. Just for completeness, I would like to mention that we discovered that there are theories beyond Hordensky that do not satisfy this requirement of second-order equations of motion, but are still ghost-free. This is an area of active research, and I'm not going to talk about that, although many of my conclusions extend to this type of theories. Now, let's start with the dark energy thing. So Hordensky is a huge theory. You have 4 functions of 2 variables. You can construct very complicated models based on that Lagrangian. But if you're interested in linear perturbations on a cosmological background, there are just 4 functions that characterize the entire physics of this model, of this class of theories. And the best way to look at these functions was proposed by Bellini and Savitsky a couple of years ago, is to look at the physical degrees of freedom. So for example, the tensors, look at the modifications that affect the tensor propagation equation and the scalar. And well, these functions are related to the main theory in a very specific way. And well, the simplest one is the kinetic term. This is for the scalar field. This is sourced by all of the Hordensky functions. We can also have terms that mix the scalar perturbations of the metric and the scalar field. This is known as kinetic mixing or kinetic gravity braiding, and this happens for all but the simplest terms in the theory. Finally, we can also have time-varying effective Planck mass that controls the strength of gravity, and this also introduces a series of effects. And finally, the most interesting of these functions is that you can affect the speed at which gravitational waves do propagate. And this is something that you really need to mess up general relativity to get this, but it appears quite naturally in this context. So we understand the cosmology. We put it in it's very dark.
Maybe we can turn.
I think it's in my laptop. So, well, we put this in maybe it's a bit better. Yeah. Well, we put this in a Boltzmann code that you can download and modify and include any model you wish within this class of dark energy models. It's publicly available, it's tested. We have a paper coming up with comparison which we show very good agreement across a range of theories and observables. And of course we can put there any theory, but probably it's better to start with what's simplest yet most interesting. And I would say that this is, in this case, is Galileo Gravity. This is a very well-known model that has been very popular for dark energy. It basically consists on taking the 3 functions and giving them the simplest, or one of the simplest dependence you can think of. In this sense, it's a simple theory, but it has all the terms and all the interactions that activate the different effects. And what's also interesting is that these Galileo models arise in a variety of contexts. So they are found in massive gravity theories as effectively describing the helicity zero mode of the massive graviton. And they also, they were actually found initially studying DGP and other extra-dimensional models. In this framework, the scalar field is the coordinate of the extra dimension, so of our 4-dimensional world in the extra-dimensional model. These theories are, they're very easy, very difficult to test in the solar system. They're very effectively screened and avoid a lot of solar system tests, but they can be tested in cosmology, and they're interesting because they provide self-accelerating solutions. Now, so we put the Galileans on high class, and we ran an analysis comparing to Planck and some BAO data, and we got the Hubble rate that we get in this way is compatible with the local determination, and like in lambda CDM, if we allow for a relatively large neutrino mass that is well within what is acceptable today. Now, Janina Renk is going to give a talk on this on the week 4. If you're not going to be there on week 4, if you're interested or you cannot wait till week 4, come to talk to us. We're happy to discuss what we have. And well, the Galilean basically has, well, we have several models that we've been testing from. The simplest one is Galileo 3 adds nothing relative to lambda CDM. It's a 0 parameter extension. Then Galileo 4 has more freedom and adds 1 parameter relative to lambda CDM, and then the complete theory in the parameter space, in this projection of the parameter space, gives this contour and has 2 extra degrees of freedom. So the focus of our paper, and as I said, I'm not going to talk a lot about this, was to see if the measurements from cross-correlation of galaxies with the cosmic microwave background that are sensitive to the ISW effect would rule out the theory as it was believed. And the answer is no. I don't know to what extent you can see this, but the green points is the region that is compatible with the ISW measurement. And these are basically the points that survive in our analysis. Now, what is interesting is that they cut down the parameter space considerably, but the Galileo 4 and the Galileo 5 still can fit the data. But the Galileo 3 gets ruled out at high significance. I think it's over 8 sigma by this ISW prediction. And this is very interesting because the Galileo 3 is the only model that predicts standard gravitational wave propagation. So if dark energy has anything to do with this, then it is inevitable to have a different speed of tensors. And this takes me to the second part of my talk. So let's take a look, showing here the equation for tensor perturbations. And there is this function, alpha t, that characterizes the different speed. And if you look at the parameter space of this theory, we can overplot the value of alpha t at the time today. And there are 2 regions, basically, one in which the gravitational waves are faster than light, and another region in which they're slower than light. So anything can happen, really, in this theory. There is a line here where the speed of gravitational waves is 0. The difference in the speed, is 0. But that is only today. And in fact, it's pretty unavoidable within these models to have a very strong signature on the propagation of gravitational waves. So here I'm plotting, this is a random sample from the models that are viable. You can see that the speed goes, can be typically from -1 to 0.4. And if you tune it to be 0 today, you still have an effect at an earlier time. So you can probe this just by going to more distant sources. And well, there is a model that has no modification throughout, but that's ruled out by the ISW effect.
Excuse me, do some line cross 0?
They can cross 0, yeah. They can cross 0, and yeah, they can cross 0 because there are 2 terms that compete. So that's why you can tune them to be 0 at redshift 0, because you cancel 2 different contributions. Now, a couple things that are worth emphasizing is that this does not affect the waveform at all. This only affects the propagation speed. So unlike, for example, the case of a massive graviton, in the case of a massive graviton, you have a frequency that depends on the wavelength with the mass, and this gives you an effect that if you have a source that has multiple frequencies, as any realistic gravitational wave event has, you can put bounds on this ng. And you cannot do that with gravitational waves alone in scalar tensor theories. You need an electromagnetic or other counterpart to compare the arrival times.
So what changes the dispersion relation is what?
It's just the speed. It's it's just a different speed. It's like but there is no minimum frequency. There is no
Different shape.
yeah. So if you have a gravitational wave that is a superposition of many frequencies generated by the source, all of them are going to be changed equally. So the only way to test this is with a counterpart. Now, the good news is that because gravitational wave sources are far away, the constraints we can get on the speed of gravity, if we get such an electromagnetic gravitational wave event, are going to be insanely precise. So I think we can have in mind a number that it's 10 to the minus 17 on the speed of gravitational waves. And recall here that what this theory predicts is 0.1. So this is huge. If there is a clear measurement in this direction, the theory will be ruled out spectacularly. No questions asked. Now, the problem is, okay, what if this theory has anything to do with dark energy, or any variation of this theory? Then you turn this equation, well, you turn it around, and then the difference in travel time is going to be 10 to the 17 times the difference in speed for a typical source, and that ends up running very easily into the millions or even the billions of years. So this program of getting gamma ray bursts and finding the pairs with gravitational waves is not going to work. So unfortunately, it's I don't think it would be, if there are no such detections, it's going to be very difficult to convince oneself that this the crazy dark energy model is behind that. So we came up, we explored an alternative route, which is to monitor periodic sources. The advantage of that is that a periodic source, it's emitting continuously, so you don't have to worry that one signal is like happened a million years before, or wait a million years for the other signal. You can get both signals at the same time. And well, the good thing is that such continuous gravitational wave sources occur. We know at least of a very excellent system. It's a binary white dwarf system that it's eclipsing, so we can measure the orbital phase very precisely. And in fact, these people measure the period of the system to a very high precision, and they even measure the time variation of the period, which is consistent with loss of energy due to gravitational waves. And well, the source is close enough that LISA should be seen like right away. And this is in fact what is known as a verification binary that people expect to use to calibrate LISA and check that everything's working fine. So the way this would work, and again, sorry for the colors, is we could have a very good measurement of the orbital phase from the eclipses in the binaries, and then some measurement of the gravitational wave signal. And we can do this for both polarizations. And if the speed is different, they're going to arrive with a different phase. And this should be, we should be able to test this up to a level of 1 part in 10 to the 12th, if we observe for 5 years. There are other effects that are not as sensitive. And what is nice about this test is that it works both ways. If we observe no phase lag, then we can test, we can put a bound on these theories, although by the time probably a gamma ray burst would have ruled them out. But we can also get a positive answer. So if there is some scalar field dark energy, this could show very strong evidence for that, especially if we get this for different binary systems. Now, the last thing I want to say is that we've also, so far what I've been talking about is cosmologically. So the cosmological perturbation theory for tensor modes, and that's how we believe gravitational waves are going to propagate on a cosmological background. However, we want to know how this happens in more general settings. And it turns out that that's feasible. We can just expand the action for linear perturbations and look at the transverse traceless part. This is the dynamical part of the metric, just as in GR, and find that it obeys it gets an effective metric that determines the propagation on which gravitational waves go. And there are two conditions that are necessary for this anomalous gravitational wave speed to happen. One is that this effective metric is not proportional to the matter metric on which light propagates. And we found that this is related to the kinetic term of the theory involving the Weyl or the Riemann tensor at the level of the equations of motion. So that's a very strong constraint on what kind of theories can produce this. And the second requirement is that the scalar field in this case spontaneously breaks Lorentz symmetry by picking a vacuum expectation value. So this, in the case of cosmology, this is going to be the time variation of the scalar field that sources the anomalous speed. And what's nice is that this gives a binary classification of alternative theories of gravity, many of which serve as dark energy models. So there are theories in which the speed of gravitational waves and the speed of light is the same exactly. That include, of course, ER, massive gravity, which has the kinetic term of ER, and also simple scalar tensor theories like Galileo 3 or Brans-Dickin. And there's also a class of theories that predict a different speed. And in general, it's going to be different, and this is something that we can test. So this type of tests are not just going to work for this simple Galilean model. They're going to potentially test a much broader range of theories. So I mentioned the Galileans and Kordensky scalar tensor theories, but this is also true for at least the best known beyond Kordensky models. And also true for bigravity, although it's a lot more subtle than what I'm explaining here. And if you're interested in that, I'm happy to tell you more about it. So in conclusion, how much time do I have? Okay. So in conclusion, we understand scalar tensor cosmology. We think this can be used to provide interesting dark energy models that can be tested in a lot of ways. So not only by the expansion of the universe, the cosmological perturbations, but also in the solar system, even maybe perhaps with some futuristic neutrino experiments, and most especially by gravitational waves. So they could be ruled out with gamma reversed, that they could have been ruled out. LIGO might be about to release some data in this direction, or if something like this is behind dark energy, they could be confirmed with NISA. Thank you.
So the first part, when you showed the solution to the H0 tension, you said you need 0.6 as the sum of neutrino masses, which, as far as I know, is pretty ruled out.
Why?
Well, it's ruled out with
Why?
lambda CDM.
It's ruled out in lambda CDM. You can see it in this plot. If you assume lambda CDM, it's pretty ruled out.
So you're saying that with this massive gravity and neutrinos of 0.6, then you solve that. Okay, and this is for all the Galilean 3, which
And
is, however, ruled out by ISW,
Right.
but also for Galilean 5.
Yeah, it doesn't change much.
So that Galilean 5 predicts a different speed of light, of
Yes.
the different speed of gravitational waves from speed of light.
Right. Yeah, I think I didn't mention it, but something, even if this model doesn't work or whatever, you don't buy it, at least bear in mind this. It's a useful reminder that H0 and some of neutrino masses are cosmology-dependent measurements. So when we quote
Here and then.
Yeah, my question is also on this. So does your fit improve enough compared to Planck to make your model better? Like, do you do some rough model comparison calculation?
Yeah, well, I think so. The chi-square difference for this, if you take the 3.4 sigma, is about 11 for 1 degree of freedom. So that's pretty bad. And our feed, when we include the newer BAO data that has some tension, I think we're roughly at that level. But I have to bear in mind that having tension on BAO is several data points.
Is this DR12, you mean, the latest GAO?
It's DR12, it's Lyman alpha. We have tension also with main galaxy sample.
MGS.
Okay. No,
Yeah, no,
which
but
one?
like in some regions of the parameter space, but like when you go to when you want to have like fits to ISW and stuff. So I think the MGS point I wouldn't worry about that. It's more DR12 and like
DR12.
So I'm just curious, if you use DR11 instead of 12, does this bad tension with BAO still persist?
I think so, right? I think the data that feed the one, I mean, we didn't want to use incompatible data in the analysis to not create artificially small constraints. I think DR11 is also in tension, although probably not as bad. The thing also that you have to bear in mind is besides the chi-square counting and phytology and whatever, is that BAO is very model independent, but you also run through BAO reconstruction, and that assumes Einstein gravity. That's a very, so in the process there is some very model dependent part. And so that's one thing. And so some data points that are in tension, they have reconstruction. The other data points that are in tension are also in tension with lambda CDM. These are the Lyman alpha points. Unfortunately, I don't have a plot to show you, but they're in tension with lambda. They're just in more tension with the Galileo.
So what is the physical reason that the sum of the neutrino masses changes to larger values?
Yeah, well, so Galileo is very, it predicts a rather negative equation of state, negative and time evolving, which would normally be ruled out. Now, if you have massive neutrinos, what massive neutrinos do is like, you can think of them as radiation that turns into non-relativistic matter. So this
compensates, right?
Yeah, this compensates partly the equation of state, and they also, at the perturbation level, neutrinos reduce the amplitude of the perturbations on small scales, and this also partly compensates the effects of modified gravity. So it's really a like roulette of effects that compensate one another.
So there's always some tuning involved, right?
In the parameters?
Yes.
Yeah, well, well, you can see that there is plenty of parameter space. The equation of state is pretty generic. There is very little room to change it. The perturbations, of course, yeah, there is tuning. Same as you can go from speed of light, gravitational waves nearly 0 to 1.5, so you can tune all the things.
Last question from
Just curious on how robust the environmental constellation data really are, first, and second, what would happen if you remove them from it, concerning the neutrino mass?
Yeah, I haven't done that. There is an earlier paper by one of our collaborators who did that. I think it's pretty much, so what you get, it's pretty much what you would get for lambda CDM, like but maybe I'm thinking omega and H naught. So I'm not sure with neutrinos, but I think it's certainly it extends. So the power is that you connect the high redshift universe and the low redshift universe by the same scale. I can look it up. And
Probably you
find
have
it.
more parameter space available.
You would certainly, yeah. I'm sure like the model without massive neutrinos, with BAO, this basically extends here, actually predicts an H naught around 77, 78. So it's like lambda CDM except here. And yeah, removing BAO, so I guess whatever does to lambda, I need to accept this place.
any other